Hello APC Mechanics students in Unit 1 Kinematics, Class 15, Projectile Motion, Part 1. Then Section 1, Projectile Motion. Projectile motion is the motion of an object projected into the air, subject only to the acceleration of gravity and frictional forces due to air resistance are neglected. So here we can see this student throwing an object, giving it an initial velocity, and along the trajectory, which is the path followed by the object, the only force would be acting on this object is the force of gravity, and in this case this is known as the projectile motion, in which air resistance is neglected. The free fall problem with or without initial velocity are special cases of projectile motion, and the path followed by the projectile, which is the trajectory, is a parabola. Remember that previously in classes 13 and 14 we have referred to specific type of trajectory, which is a parabola, in which one of the positions is quadratic in time and the other is linear, and this happens whenever the motion is dictated by such conditions. Now we will differentiate between two types of projectiles, symmetric projectile and non-symmetric projectile. In the symmetric projectile, the thing is that the launching point and the landing point would be the same. So the problem starting from a clock at t is equal to 0 starts from here. That would be the launching point. The projectile will follow a parabolic trajectory and it will land at this point. If the launching and the landing point is at the same height, then this is a symmetric projectile. Otherwise, that would be a non-symmetric projectile where the launching and the landing point are at different heights, and this would be a perfect example for like throwing an object from a cliff. Now, section 2, descriptive projectile. A projectile is launched with initial velocity into the air, so we need to analyze what's happening to the velocity. Now, what vector affects the velocity? Basically the acceleration. The acceleration is responsible for generating the velocity vectors. Now if you look carefully at the animation from the launching point to the landing point, if you look at Vx, the magnitude of Vx, it's not changing and the direction is not changing at all, simply because along the x-axis we don't have any force. Now the only force acting on such a motion is the pull of gravity, which is downward, and along the x-axis we don't have any force. So for that reason we expect along the x-axis the velocity would remain unchanged, whereas for the vertical velocity, because the acceleration is downward, so we're gonna notice that along the upward motion the vertical velocity will decrease until it momentarily vanishes, then it will be generated back again. So let me by that repeat and say, during the upward motion, the acceleration, because it's pointing downward, it will destroy the vertical velocity until momentarily reaches 0. Then back again, during the downward motion, it will start to generate it, similar to the free fall with an initial launch upward. Now we're still in section 2, descriptive projectile. Now we're gonna discuss the acceleration. At all instants along the motion of the projectile, the horizontal acceleration is given by 0. So let's consider the object at different points along the trajectory. Now in this case, at all points, ax is set to be 0. Now what about the vertical acceleration ay? Along the y-axis is given by 10 meters per second squared downward, or negative 10 meters per second square. Then ay is given by negative 10 meters per second square. So at all points of the projectile, the acceleration is given by 10 meters per second squared downward. Now what about the velocity? The velocity of the projectile is, so let me consider the object at different points of the trajectory. The horizontal Vx along the x-axis remains constant at all times. Now this comes from the fact that ax is 0, so I have represented here the components of the acceleration ax and ay. Now this is the launching point, then we're launching the projectile with an initial velocity making an angle suppose 30 degrees with the horizontal. From that we can determine the horizontal velocity using projections. Then we have decomposed v into Vx, and along the motion Vx would remain constant at all times. The vertical velocity Vy along the y-axis decreases at a rate of 10 meters per second, and this is because the acceleration is pointing downward, and partly it will destroy Vy until it momentarily becomes at rest, then it will generate it back downward. So Vy initially can be determined by decomposing V along the y direction. Along the upward motion, it will decrease until momentarily becomes 0, then it will be generated back again. Now what about the maximum height? This would represent the maximum height reached by the projectile. The maximum height of the trajectory has a vertical velocity Vy is equal to 0, while the horizontal velocity Vx remains unchanged. We are now familiar with the fact that maximum height is determined by vanishing velocity. Here Vx cannot vanish because it's constant along the motion. The only velocity or the component of the velocity that can vanish is the vertical velocity because it is the one which is changing. Then in order to determine the maximum height of the projectile, we need to use the constraint equation, which is given by Vy is equal to 0. So that would be the maximum height. Another important idea to notice is that slices of same height carry the same speed but different velocities. Speeds are the same but directions are opposite. Consider the following two positions given by 1 and 2. They lie at the same slice of height. So you can notice that Vx at all points is constant, and in particular 1 and 2. Now what about Vy? Vy here in magnitude both would be the same. So let me say, for example, that would be 3 meters per second and 3 meters per second. In magnitude they would be the same, but as velocities that would be plus 3 meters per second and that would be negative 3 meters per second. So in velocities Vy would be opposite, but in magnitude that would be the same. So for the same slice of height, the speed, which is the Pythagorean sum of Vx and Vy, would be exactly the same. What is different is just the velocities, and they would be the vertical would be the opposite. Now also if you consider this slice of height, similarly here Vx is constant because Ax is 0. Now what about Vy? Here it's pointing up, so we can say that this is, for example, plus 5 meter per second and this is negative 5 meter per second. In magnitude they are the same, but however the directions are opposite. If you consider the speed, which is the total speeds for x and y, that would be exactly the same, and this holds true for the initial and for the launching and the landing points of the projectile. Now section 3, position, velocity and acceleration, time graphs of a projectile. This is also a very important section. It is important to remember the shape of the curves of a projectile motion. We will consider two orientations. First case, the positive x direction is pointing right and plus the positive y direction is pointing up. In all the cases, we're gonna consider positive x to be to the right along the motion of the projectile. However, we have two cases. Either the y direction to be up, so positive is up, or positive will be considered to be down. How this would affect our equations of motions? Remember that in the equations of motion, the acceleration appears as a component either ax or ay, and that would affect the acceleration up to a minus sign, and let me explain more. Gravity is always pointing down. If you consider the first case in which y is up and we know that gravity is down, then in this case ay would be given by minus g, which is negative 10 meter per second square, because they are in opposite directions. However, if the positive y direction is chosen to be down, that would affect the component of the acceleration, and this is given by plus g, which is 10 meter per second square. And now we're considering the case where the positive direction is up. Now we know that the vertical acceleration, okay, before I discuss that, let me write the order that we follow in such interpretations: from 0 to constant, to linear, to quadratic, and that would be a to v to x. Along the vertical direction, the acceleration is constant. Because the positive direction is up, then ay would be negative, and it has been represented by a horizontal line, which is constant. Now if a is constant, we expect that v is gonna be linear. Linear means it's gonna be either like this or like that. A is negative, which means the velocity is decreasing, and that would be the shape of the vt graph, in particular vyt graph. Here we're analyzing the motion along the y direction. Now if v is linear, then x would be quadratic. The shape of a quadratic curve would be something like this or like that, because the acceleration is negative, then it's gonna be up and downward. Then it would be something like this. And in particular, let's check. Initially the velocity is positive, so I'm dividing it to several portions. That would be positive, so the vertical position would increase, and after that it momentarily becomes to a stop, so the vertical position would do something like this. And after that the velocity is negative, which means that the position will decrease, and we expect that the shape for a YT graph would be something like that. What about the horizontal motion? Ax is 0 because no acceleration along the x-axis. Then, and we know that the positive x direction is considered to be along the direction of motion, and by that case, if a is constant, then if a is 0, then v is constant and it is shifted upward. If v is constant, then the position would be linear, either like this or like that. This is positive, which means the position is increasing, then the shape of the xt graph would be something like that. And here, if you look at the xt graph, I have represented it with a straight line starting from the origin, and this is because the launching point would always coincide with the initial position is equal to 0, as we shall see. What about the second orientation, in which the positive direction is chosen to be downward? Let me first write that 0 to constant, to linear, to quadratic, and that would be a to v to x. If the positive y direction is chosen to be downward and gravity is down, then ay in this case is given to be constant and positive. Then the shape ayt graph would be something like that. Ay is constant, which means v is gonna be linear, so it's either like this or like that. This is positive, then that would be the shape of the vt graph. You can split this into two portions. This is the first portion, and that would be the second portion. Initially vy is set to be negative, and after that initially it's negative, and after that it's positive. This is linear, the position is gonna be quadratic, either like this or like that. The acceleration is positive, so it's gonna be up and upward. Now initially it's negative, so the vertical position will decrease, momentarily becoming at rest, and after that it would increase. Then we expect that the vertical position would have a shape like that. As for the horizontal position, it would remain unchanged because ax is 0. We're choosing the positive direction along the direction of motion. Vx is positive, and that would give us a linear position xt graph. Now section 4, equations of motion for a projectile. Now we have reached a point that we're ready to analyze the projectile problem analytically using equations of motion. The projectile problem will be analyzed solely along the x-axis and the y-axis. So the thing is that because along the x-axis the type of motion is uniform, because ax is 0, we're gonna analyze it solely along the x-axis, and then we're gonna analyze it along the y-axis because it's uniform varied motion due to a constant acceleration pointing downward. Consider a projectile launched with an initial velocity v0 making an angle theta above the horizontal. So that would be our choice for the xy system. Notice that my choice stands for the positive y direction to be up. Then in this case ay is given by negative g. And remember that all of the work and the results that we're gonna derive only holds for a positive direction to be upward, and you can deduce the equations for positive y direction to be downward by switching negative g into g. We have a projectile launched with an initial velocity making an angle theta with the horizontal. So that would be the trajectory, which is a parabola. Now we need to dictate this trajectory using equations of motion. Along the x-axis, the horizontal acceleration is 0, then the type of motion is uniform along the x-axis, and we know that in this case we can only use one equation of motion, which is given by x is x0 plus vxt. Now here the initial position coincides with the origin, so we can replace x0 by 0, but we're gonna keep it like that. What about vx? Vx is constant at all instants, but the only velocity that we know about is the initial velocity. So Vx is equal to Vx for all instants of time, and in particular Vx0. What does Vx0 represent? It is the projection of V0 along the x-axis. And how do we project it or decompose it along the x-axis? Then this is geometrically and analytically, that would be V0 multiplied by cosine theta. That would be Vx or V0 along the x-axis, where Vx is constant and can be determined from the initial velocity. Then Vx is Vx0, which is V0 cosine theta, and now we're done with the motion along the x-axis. So we suppose we know the initial velocity and the launch angle, then this equation can be written in the form x is x0 plus V0 cosine theta t, and remember that this represents Vx. So Vx is V0 cosine theta t. So along the x-axis we have two equations that we can play with. The position related to time, and Vx is V0 cosine theta. Now what about the y-axis? The problem here is more complicated. The vertical acceleration ay is given by minus g, then the type of motion is uniformly varied along the y-axis. Why it's uniformly varied? Because ay is given to be a constant. Now in this case, we know that the vertical position related to time is given by y0 plus vy0t plus half ayt square. Now here in this case, we know that y0 is set to be the origin, which is 0, so we can replace that by 0, but we're gonna keep it for a more general representation, where vy0 is the initial vertical component of the velocity. So we are interested in determining, so this should be 0. Let me correct it. Now in the equation of motion we have vy0. How to determine vy0? Vy0 is related to the initial instant, which is here, and represents the projection of V0 along the y-axis. And if this is cosine, then that would be sine, so Vy0 would be V0 sine theta. And replacing this result in the above equation of motion, and ay would be replaced by minus g, then the vertical position in terms of time is given by that. The other equation of motion, so remember that this is one of the equations of motions. The another equation would be given by Vy is equal to Vy0 plus ayt, then ay is given by negative g, and V0y is given by V0 sine theta. Then the other equation of motion will be given by Vy is V0 sine theta minus gt. And now by that we can summarize the results for a projectile motion in which the positive direction is chosen to be upward. Along the x-axis, x is x0 plus V0 cosine theta t, and Vx is V0 cosine theta t. Along the y-axis, y is y0 plus V0 sine theta t minus half gt square, and Vy is V0 sine theta minus gt. Section 5, the maximum height problem. The following works for both projectiles, symmetric and non-symmetric projectile. Here in this section we are interested in determining the maximum height. And now whenever we're trying to achieve a result, we should always cite the fact that whether this works for symmetric or non-symmetric projectile. Now in this case, this works for both types of projectiles. The maximum height is determined by the constraint Vy is equal to 0, but now we know that Vy is given by V0 sine theta minus gt. Then setting it equal to 0 and solving for time would be given by V0 sine theta divided by g. We have the time, so what does this time represent? This is the time it requires to reach the maximum height, and now we can replace it in the vertical position given by y is y0 plus V0 sine theta t minus half gt square. So we're gonna replace the time which is given by V0 sine theta divided by g in this equation. And in most of the cases, we consider the launching point to be the origin. So we will say that this is the origin. So y0 is 0. And the vertical position in this case would be replaced by capital H, which is the maximum height. So y is replaced by the maximum height. The initial position is replaced by 0. Here notice that t has been replaced by V0 sine theta over g. And t also here would be replaced by the same, and we have to the power of 2. So in this case, what do we have? We have v0 multiplied by v0, which is v0 squared, sine theta multiplied by sine theta, sine squared theta, divided by g, minus half, and this power 2 is 4, the numerator and the denominator, and that would be v0 squared, sine squared theta, divided by, here we should have, okay, that would be divided by g squared, but this cancels with this, we're left with the g. And here notice that for this step, we have 1, the factor here is 1, and we know that 1 minus half, that would give us 1. For this reason, the final result, which is the maximum height, is given by v0 squared sine squared theta divided by 2g. So in brief, for both symmetric and non-symmetric projectiles, the maximum height would be given by v0 squared sine squared theta divided by 2g. Okay, and that would be the maximum height. So what are some interpretations or remarks for maximum height? Now the only two variables that appear in the maximum height are v0 and sine theta t. The sine theta function is an increasing function from 0 to 90 degrees. So as the angle increases from 0 to 90, the sine theta function will increase, which means sine square would increase, and that would increase the maximum height. The maximum value occurs whenever theta is equal to 90 degrees. So if theta equals to 90 degrees, that would mean sine theta is equal to 1, because sine 90 is equal to 1, and that would reduce the problem as if we're launching. So it will be a free fall with an initial launch upward. So as the launch angle theta increases, the maximum height h increases, and as the launch velocity v0 increases, the maximum height h increases as well. Everything here holds true for a symmetric and non-symmetric projectile. Now let's start with the exercises. Exercise 1. A small sphere is thrown through the air and follows the parabolic path shown in the figure. Point P is the highest point the sphere reaches. Assuming air resistance is negligible, which of the following claims is true of the sphere while it is in motion? Now I'm gonna go all the choices and try to interpret each one. A, the vertical component of the sphere's velocity is at maximum at point P. This is perfectly wrong, because we know that the vertical component of the sphere's velocity at P, it's not maximum, however it is 0. B, the horizontal component of the sphere's velocity is 0 at point P. This is wrong. We know that the horizontal component of the sphere's velocity is constant everywhere, and it's not 0 at P. Vy would be 0 at P. The acceleration of the sphere is constant. This is true because we know that Ax is 0 at all times, and Ay is equal to some constant, either plus g or minus g, which is constant at all times. So C would be the correct answer. The sphere's speed is constant. No, it's not constant, it's changing under the influence of gravity. The displacement of the sphere is 0 at point B. No, we can calculate some displacement from the launch point to the point P. Now exercise 2, a ball is thrown and follows a parabolic path as shown above. Air friction is negligible. Point Q is the highest point on the path. Which of the following best indicates the direction of the acceleration, if any, of the ball at point Q? We know that the acceleration along the trajectory of the projectile always points downward, then C would be the correct choice. This holds for any point along the trajectory, independent of P, Q, or any other point. Exercise 3, which is the last exercise of today's video as an exit ticket. A projectile is launched from the ground with an initial velocity of 12 meters per second. Then let me write it down. The initial velocity is given by 12 meters per second at an angle of theta is equal to 30 degrees above the horizontal. This is important for the sketch because we know that we can launch the projectile in two manners, either above or below the horizontal. The projectile lands on a hill 7.5 meters away. This is important. The height at which the projectile lands is most nearly, so we're interested in determining the height. Before I start proceeding with the solution, let's do a sketch. Then this is the x-axis and this is the y-axis. So we have chosen the positive y direction is to be up in order to make use of the equations of motions we have derived previously. We're launching the projectile with an initial velocity 12 meters per second, making an angle 30 degrees. So it will follow a parabolic path like this. Let me erase these. Alright, but however, it's not gonna continue its path, because here it will hit a hill, and they're telling us that the hill is 7.5 meters away. Away means horizontal distance, so this would be 7.5 meters. And we're interested in the height at which the projectile lands, basically the height at the impact point. Now let me write the equations of motions that we have for a projectile motion. Along the x-axis, we have that x is x0 plus v0 cosine theta t, and basically vx is v0 cosine theta. And along the y direction, we have y is y0 plus v0 sine theta t minus half gt square, and vy would be given by v0 sine theta minus gt. Now let's suppose that the launching point coincides with the origin. Then this is 0 and this is 0. What do we have here? We have the initial speed, we have the launching angle, and we have the horizontal distance. Basically, how we're gonna think, or how we're gonna analyze the problem, since we have x, then from x we can determine t, and if we have t, we can determine y. So let me show you. Using this equation, which is given by x is equal to v0 cosine theta t, we can isolate t. Then t would be given by x over v0 cosine theta. Now what would this instant time represent? This is the instant time at which, or at the impact point. Now the value of x is given by 7.5. The initial launch is 12 cosine 30. Plugging this on the calculator, that would give us a 0.72 seconds. That would be the time required for the projectile to impact the hill 7.5 meters away. Now we have the time. The time can be replaced in the vertical position. The vertical position is given by v0 sine theta t, which is 12 sine 30 multiplied by the time, which is 0.72, minus half gravity is given by 9.81 multiplied by 0.72 to the power of 2. Plugging this expression on the calculator, we're gonna have a vertical position given by 1.78 meters almost. Then in this case the correct answer would be A. Then that's it for me in this video, guys. See you soon in a new one.